This conference will now be recorded.
Good afternoon, all. We will start with our session. Can you please tell whether I'm audible? Could anyone confirm if I'm audible?
Yes, ma'am, audible.
Audible.
So, good afternoon, all. We will start with our session. In today's session, I'm going to give a demo on design for testability, DFT. So, before we go into what is DFT, we'll first try to understand what is VLSI. VLSI stands for Very Large Scale Integration. So it is implementation of million transistors in a small area. Okay, uh, just a second. So it is nothing but implementation of million transistors in a small area. So goal of VLSI means if a particular company is designing a chip, then they will be having some primary conditions that has to be met. So that is what is the goal of VLSI. Okay. So goal of VLSI is first one is high performance. So ensuring faster processing. Second one is low power consumption. So optimizing power usage to extend the battery life. Okay. Optimizing power usage to extend the battery life. And then low area or a minimal area. So reducing chip size to achieve compact products. And this is how our chip will look like. And next we'll go to the ASIC flow. So the full form of ASIC is application specific integrated circuit. So which means the IC which we are designing, the integrated circuit, the IC which we are designing, it will be specific to a particular application. For example, a modern chip, it cannot be used as a chip which is responsible for deployment of airbag in your automobile. A modern chip, it cannot be used as a chip which is responsible for deployment of airbag in your automobile. So that is why we are saying it is application specific integrated circuit. The IC which we are designing, it will be specific to a particular application. And ASIC flow. ASIC flow, it actually gives the steps which we need to follow for designing a chip. So these are all the steps which is involved in the process of chip design. So in the upcoming slides, we'll discuss about the various steps which is involved in the process of chip design. Okay. So the first phase is the design specification stage. So design specification stage, like based on the application for which we are designing the chip, certain specifications will be decided like what has to be the speed, how many memory modules, processors, sensors are required, what has to be the power. So such kind of specifications will be decided during the design specification stage. And one more thing, if in case my voice is not audible or like if my voice is breaking or something, you can unmute yourself and tell because while I'm presenting, the chat box is not visible to me. So that's why you can unmute yourself and tell if in case like my voice is not audible or something. Okay. So let's continue. So design specification stage means like based on the application for which we are designing the chip. So based on the application for which we are designing the chip, certain specifications will be decided, like what has to be the speed, how many memory modules, how many memory modules, and then processors, sensors are required, okay, and then what has to be the power, So such kind of specifications will be decided. Okay. So based on the application for which we are designing the chip, certain specifications like what has to be the speed, how many memory modules, processors, sensors are required, what has to be the power. So such kind of specifications will be decided during the design specification stage. After that, we have the design code stage. So design code, it will actually be done by the design team. So they write the design code of the chip. They describe the functionality of the chip. And this design code, it will be in behavioral model or data flow level model. So the design code will be in behavioral model or data flow level model. Behavioral model or data flow level model. And after this, we have the verification team. So after this, we have the verification team. So verification team, they validate the functionality of a design to ensure that it meets the required specification and performs as intended. So that is what is the task which is done by the verification team. Okay. They validate the functionality of the design. Validate the functionality of the design to ensure that it meets the required specification. It meets the required specification and performs as intended. And then we have the synthesis stage. So during the synthesis stage, the behavioral and data flow level model code, it will get converted to structural form, or we can call it as technology node specific gate level netlist. Okay. So sorry, the behavioral and data flow level model code, behavioral model or data flow level model code, it will get converted into structural form. Structural form, or we can call it as technology node specific gate level netlist. And after that, we have the design for testability team, DFT team. So DFT team, we insert some test structures into the design during the pre-silicon stage to
Ma'am, your
facilitate
voice
the.
is breaking a lot.
Okay, let me check.
It's
Okay, just a second, let me check. Is my voice clear now? Am I audible? Is my voice clear? Am I audible? Is my voice clear?
ma'am, you are audible, but your voice is cracking so much. It is not that sound.
Okay, just a second, let me check. So how about now? Am I audible? Is my voice clear?
Yeah, we can hear you, but can someone else suggest what they are hearing? Because for me, it's cracking so much. I don't know.
Is my voice breaking for everyone, or a few of you are facing that problem? Can someone else confirm? Is my voice cracking? So how about others? Is the problem same for everyone? So two people have said that my voice is breaking. Is the problem same for everyone? Can someone else also confirm? Okay. 1 second. I just connect to a different network. Just a second. I am joined through a different network. Can anyone confirm if I am audible now and is my voice clear or is it breaking? Am I audible? Is my voice breaking? Uh, is my voice clear? So shall we proceed? So can anyone confirm?
Yes, ma'am, clear.
Okay, so we can proceed now. So design for testability team, that is DFT team. So DFT team, we actually insert some to the design during the pre-silicon stage. Facilitate the detection of manufacturing of the chip. We'll try to explore about design for testability more in detail in the future slides. Okay, so design for testability DFT, we insert certain test structures into the design during the pre-silicon stage to facilitate the detection of manufacturing defects in the chip. We'll try to explore more on design for testability in the upcoming slides. And after that, we have the physical design. So physical design team, they convert the gate level netlist into layout form. Okay, physical design team, they convert the gate level netlist into layout form. So that is the role of the physical design team. So they convert the gate level design, convert the gate level design into layout form. Gate level design into layout form. Okay. And after that, we have sign off. So in sign off, we have STA, physical verification, PD, and logical equivalence check, LEC. So STA, the full form of STA is static timing analysis. As its name suggests, it is a method of validating the timing performance of a design by checking all possible paths for timing violations. So STA, full form of STA is static timing analysis. It is a method of validating the timing performance of a design by checking all possible paths for timing violations. And then we have the physical verification PV. So it is actually to verify layout of the circuits. And then we have LEC, logical equivalence check. So logical equivalence check, LEC, it is actually done in order to check whether the final design is logically equivalent to the original design. So our design, it actually undergoes a lot of changes in each stage. So if you see, we first had the behavioral and data flow level model form. And at the time of synthesis, it got converted into a structural form, or we can call it as a technology node specific gate level netlist. And if you want to go for low power design, then we need to add up some extra cells like clock gating, then retention registers, isolation cells, some kind of special cells we need to add it into our design when we want to go for low power design. And same way at the time of DFT, we will be adding our own test structures into the design, like scan insertion, MDIST insertion, boundary scan insertion. Like that, we'll be adding our own test structures into the design. So if you see our design, it is undergoing a lot of changes in each stage. So that's why LEC is done to check whether the final design is logically equivalent to the original design. Okay, LEC is done to check whether the final design is logically equivalent to the original design. So for that reason, we'll be doing the LEC. So if you see, our design is undergoing a lot of changes in each stage. So LEC is done to check whether the final design is logically equivalent to the original design. And LEC will be actually performed after each step, like after synthesis, after DFT, after PD, like that LEC will be done after each stage. And finally, we have the tape out. So tape out means delivering the database to the manufacturing unit. So that is what is tape out. Okay, tape out means delivering the database to the manufacturing unit. Delivering the database to the manufacturing unit. And finally, we have packaging and testing. So packaging and testing will be done after manufacturing. Packaging and testing will be done after manufacturing. Okay. So what is packaging? If you see, this complete circle will be called as the wafer, and each individual portion is called as a die. Covering this die with a protective layer is called as packaging. Covering the die with a protective layer is called as packaging. And testing, it is actually done to check whether our device is good or not, whether our chip is good or not, whether there are any manufacturing defects or not. So in order to check that, we'll be doing the testing. Okay, packaging and testing is done after manufacturing. So if you see, this complete circle is called as a wafer, and each individual portion, each small portion, it is called as a die. So covering the die with a protective layer is called as packaging. And testing, it is actually done to check whether our chip is good or not, whether there are any manufacturing defects or not. Okay, so this is what is the complete ASIC flow. And in the upcoming slides, we will discuss more in detail about the verification team, design for testability team, and also about this testing. Okay, we'll also try to understand the differences between the verification team and then the DFT team, and why we need both functional verification team as well as DFT team. So we'll try to cover all these things. We'll try to explore all these things in the upcoming slides. We'll try to explore more in detail about the verification team, the design for testability team, and also about this testing. Okay. So what is DFT? DFT, it is actually to insert test structures into the design. So we will be inserting our own test structures in the design, like scan insertion, MBIST insertion, boundary scan insertion. Like that, we will be adding our own test structures in the design during the pre-silicon stage. Pre-silicon stage means before manufacturing. Okay? Pre-silicon stage means before manufacturing. Okay. To facilitate. To facilitate means to help. To help in the detection of manufacturing defects in the chip. So which means if suppose a particular chip, okay, so if suppose a particular chip, if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell will be able to tell what manufacturing defect has caused the chip to fail. What manufacturing defect has caused the chip to fail. Okay. So DFT, it is actually to insert test structures in the design. We'll be adding our own test structures like scan insertion, MBIST insertion, boundary scan insertion. Like that, we will be adding our own test structures in the design during the pre-silicon stage. Pre-silicon stage means before manufacturing. To facilitate, which means to help detection of manufacturing defects in the chip. So if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, so if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, and what is the role of DFT engineers? So as we discussed, DFT is to insert test structures in the design during the pre-silicon stage to facilitate detection of manufacturing defects in the chip. Okay, so as we discussed in the previous slide, the same thing we had discussed it in the previous slide. So DFT engineers, we do not check the functionality of the chip. We rather check the quality of the chip. DFT engineers, we do not check the functionality of the chip. We rather check the quality of the chip. So in the upcoming slides, let's try to explore about this further. Like we'll try to understand this point through some examples, and we'll also try to understand like what is the differences, what are the differences between the DFT engineer and functional verification engineer's role, And why do we need both DFT team as well as the functional verification team in the upcoming slides? Okay, just a second. It should be like this. Yeah. So we'll try to understand this point. So DFT engineers, we do not check the functionality of the chip. We rather check the quality of the chip. So let's try to understand this point through an example. And we'll try to explore this point through an example. And we'll also try to understand what is the difference between a DFT engineer and a functional verification engineer. And why do we need both DFT engineers as well as a functional verification engineer? Okay. So consider the case of a half adder. So if you consider a half adder design, so how do we write? So we write it like sum is equal to A XOR with B, carry is equal to A. That is what is a half adder design, right? Sum is equal to A XOR with B, carry is equal to AB. So whether this is correct or not, whether this is correct or not, that is what will be checked by the functional verification team. So in our ASIC flow, we also had a team called as a verification team, right? So this is what will be checked by the functional verification team. They will be checking the functionality. Okay, so half adder design means if it is sum means we'll be writing it as A XOR with B, carry is AB. Whether this is correct or not, whether this is correct or not, that is what will be checked by the functional verification team. They will be checking the functionality. So by mistake, if someone has written sum is equal to A plus B, carry is equal to AB, by mistake, if someone has written like this, then it will not function like a half adder. Okay, by mistake, if someone has written like sum is equal to A plus B, carry is equal to AB, then this will not function like a half adder. So these things is what will be checked by the functional verification team. They will be checking the functionality. Okay, so if you consider a half adder design, sum is A XOR with B, carry is AB. Whatever is written, whether this is correct or not, that is what will be checked by the functional verification team. They will be checking the functionality. So by mistake, if someone has written sum is equal to A plus B, carry is equal to AB, this will not function like a half adder. So this is what will be checked by the functional verification team. They will be checking the functionality. DFT team, we do not check the functionality. We check whether each and every net of the half adder is free of defects or not. Okay, so DFT team, we do not check the functionality. We check whether each and every net of this half adder is free of defects or not. So say for example, this is our intended design. So A and B, it is XORed and that is nothing but your sum. And A and B, it is ANDed, so that is nothing but your carry. So A and B is actually coming from some flops and sum and carry, it is going back again to some flops. So this is what is your intended design. Now during manufacturing, say for example, unintentionally during manufacturing, A net of this AND gate got connected to ground. Okay, unintentionally during manufacturing, A net of this AND got connected to ground. So these kind of things is what will be checked by the DFT team. So DFT team, we do not check the functionality. We check whether each and every net of this half adder is free of defects or not. Okay, so this is the intended design. So so A and B, it is XORed and that is your sum. A and B, it is ANDed and that is your carry. So A and B, it is coming from some flops and sum and carry, it is going back again to some flops. So during manufacturing, unintentionally during manufacturing, A net of this AND gate got connected to ground. Okay, unintentionally during manufacturing, A net of this AND gate got connected to ground. So these things is what will be checked by the DFT engineer. We do not check the functionality. We check whether each and every net of this half adder is free of defects or not. Okay, unintentionally during manufacturing, any of this AND gate got connected to ground. So these things is what will be checked by the DFT team. We do not check the functionality. We check whether each and every net of the half adder is free of defects or not. Okay. So let's try to take one more example and let's try to understand more in detail about what is the difference between a DFT team and a functional verification team's role, and why do we need both DFT team as well as a functional verification team. So let's try to take another example and we'll try to focus more on that. So why do we need a DFT team? Why do we need a DFT team when we have a functional verification team? Okay, why do we need a DFT team when we have a functional verification team? So let's take this example. So you're having a design. So in your design, you're having a 10-bit counter with a counter initialization and a counter observation circuit. Okay, you're having a design. In your design, you're having a 10-bit counter with a counter initialization and a counter observation circuit. Now, suppose the counter is manufactured with a defect. Okay, suppose the counter is manufactured with a defect. So, which means after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Okay, so suppose if the counter is manufactured with a defect. So, that's why after counting 999, it has to count 1000. But instead of counting 1000, it is once again counting 999. Okay, so after counting 999, it has to count 1000. But instead of counting 1000, it incorrectly rolls back to 999. Okay, it is once again counting 999. We'll try to explore what will happen if only functional verification team exists and what will happen if a DFT team exists. Okay, we'll try to explore what will happen if only functional verification team exists and what will happen if a DFT team exists. So if only functional verification team exists, what will happen? We'll first try to understand. So what is the scenario we are considering? So we are having a design. In my design, I'm having a 10-bit counter with a counter initialization and a counter observation circuit. The scenario I'm considering is, suppose the counter is manufactured with a defect. Okay, say that the counter is manufactured with a defect. So that's why after counting 999, instead of counting 1000, it once again counts 999. It incorrectly rolls back to 999. So this is the scenario. Okay, so the counter, it is manufactured with a defect. That is the reason why after counting 999, instead of counting 1000, it incorrectly rolls back to 999. Okay, so now in this case, if only functional verification team is existing. Okay, just imagine that only functional verification team is existing. So what will happen? Functional team, they test the counter with functional patterns. Okay, functional team, they will test the counter with functional patterns. So if functional team, if they test the counter with functional patterns, then it will take more than 1000 clock cycles. It will take more than 1000 clock pulses to tell that the counter is failing. It will take more than 1000 clock pulses to tell that the counter is failing. And why is it like that? Any guesses? So why it will take more than 1000 clock pulses to tell that the counter is failing in this case? So like if functional team tests the counter with functional patterns, so it will take more than 1000 clock pulses to tell that the counter is failing. So any guesses like why it is like that? So as you know, functional verification team, they actually check the functionality. Okay, the reason is functional verification team, okay, they will be checking the functionality. Okay, functional verification team, they check the functionality. That is, they check if the counter counts from 0 to 1023 in this case. Okay, so in this case, in my example, I have considered a 10-bit counter, right? So functional verification team, they check the functionality means they will check if the counter properly counts from 0 to 1023. Okay. So they will check that is in this example, they check if the counter counts from 0 to 1023. They check if the counter counts from 0 to 1023. Counts from 0 to 1023. Okay. So now in this case, what is happening? The counter is failing at the 1000th pulse. So at the 1000th pulse only, instead of counting 1000, it incorrectly rolls back to 999. It once again counts 999. So counter is failing at the 1000th pulse. Okay, so in this example, counter is failing at the 1000th pulse. Because at the 1000th pulse only, instead of counting 1000, it is once again counting 999. So counter is failing at the 1000th pulse in this case. Okay, so counter, it is failing at the 1000th pulse. The counter is failing at 1000th pulse. Okay, so that is at the 1000th pulse. That is at the 1000th pulse. Counter is again counting 999 instead of 1000. Counter is again counting 999 instead of 1000. Okay, so 1000 pulses are required for this. Okay, 1000 pulses are required for this. And then some more clock pulses. Some more clock pulses will be required for counter initialization and counter observation. So counter initialization means the counter, it has to be brought to some initial state. Counter observation means the output of the counter, it has to be taken to some register and the register has to be read. So that's why some more clock pulses will be required for counter initialization and counter observation. Okay. So some more clock pulses are required for counter initialization and counter observation. Okay. So that's why functional verification team, they require more than 1000 clock pulses to tell that the counter is failed. Okay, because functional verification team, they check the functionality. So in our case, we are having a 10-bit counter. So that is why functional verification team, they check if the counter counts from 0 to 1023. So in our example, what is happening? Counter is failing at the 1000th pulse. So at the 1000th pulse, counter is again counting 999 instead of 1000. So counter is failing at the 1000th pulse. So 1000 pulses are required for this. And some more clock pulses are required for counter initialization and counter observation. Okay, some more clock pulses are required for counter initialization and counter observation. So counter initialization means counter has to be brought to the initial state, and counter observation means the output of the counter, it has to be taken to some register and the register has to be read. So some more clock pulses are required for counter initialization and counter observation. So ultimately we can say that functional verification team, it will take more than 1000 clock pulses to tell that the counter is failing. And then functional verification team, they can only tell that the counter is failing. Okay, functional verification team, they can only tell that the counter is failing. Why? Because see, functional verification team, they check the functionality. Okay, functional verification team, they check the functionality. check the functionality. Okay, so that is they will check if the counter counts from 0 to 1023 properly or not. So in this example, okay, they check the functionality means that is in this example they will check whether the counter properly counts from 0 to 1023. Check if the counter counts from 0 to 1023 properly. Counts from 0 to 1023 properly. Properly or not. Okay. So in this case, what is happening after counting 999, instead of counting 1000, it is once again counting 999. So that's why the counter is failed. Okay, in this case, what is happening? In this case, after counting 999, after counting 999, instead of incrementing to 1000, instead of incrementing to 1000, it once again counts 999. It is once again counting 999. Okay, so that's why the counter is failed. That's why the counter is failed. Okay, so let me just summarize the point. Whatever I have told now, let me just summarize before we proceed further. Okay, so I am just considering a design. So in my design, I'm having a 10-bit counter with a counter initialization and a counter observation circuit. Okay, so suppose the counter is manufactured with a defect. Okay, so suppose the counter is manufactured with a defect. So after counting 999, instead of counting 1000, it incorrectly rolls back to 999. It is once again counting 999. Okay, so this is the scenario which I'm considering. So suppose the counter is manufactured with a defect. So after counting 999, instead of counting 1000, it is once again counting 999. We'll try to understand what will happen if only functional verification team exists, if a DFT team also exists. Okay, we will try to understand what will happen if only functional verification team exists and what will happen if a DFT team also exists. So, if only functional verification team exists. Okay, so if only functional verification team exists. So, in our case, what is happening? Counter is manufactured with a defect. So that's why after counting to 999, instead of incrementing to 1000, it again counts 999. It incorrectly rolls back to 999. So suppose functional team, so you imagine that you only have functional verification team. So functional team, they are testing the counter with functional patterns. Okay, so functional team, they are testing the counter with functional patterns. Okay. So in this case, it will take more than 1000 clock pulses to tell that the counter is failing. Why? Because functional verification team, they check the functionality. So in this case, they will check whether the counter properly counts from 0 to 1023. So the counter, it is failing at the 1000th pulse, because at the 1000th pulse only, instead of counting 1000, it is once again counting 999. So 1000 pulses are required. And some more clock pulses will be required for counter initialization and counter observation. So counter, it has to be brought to some initial state. And then the output of the counter, it has to be taken to some register, and the register has to be read. So some more clock pulses will be required for counter initialization and counter observation. So that's why ultimately we can say that functional verification team, they require more than 1000 clock pulses to tell that the counter is failed. And functional verification team, they can only tell that the counter is failed. The reason is because they will be checking the functionality. So in this case, they will check whether the counter properly counts from 0 to 1023 or not. So in our case, after counting 999, instead of counting 1000, it is once again counting 999. So the counter is failed. That's it. Functional verification team, they can only tell that the counter is failed. Now, if you consider that we also have a DFT team. Okay, consider that we also have a DFT team. Same scenario, I'm having a design which is a 10-bit counter with a counter initialization and a counter observation circuit. So the scenario is, suppose the counter is manufactured with a defect, which means after counting 999, instead of incrementing to 1000, it incorrectly rolls back to 999. Okay, counter is manufactured with a defect, so that's why after counting 999, instead of counting 1000, it once again counts 999. Now, in the second case, we are considering what will happen if a DFT team exists. So, if DFT team exists, then what will happen? DFT patterns are used to test the chip. Okay. So, if DFT team exists, DFT patterns are used to test the chip. So, DFT team, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses. Okay, DFT team, we will be able to tell that the counter is failing in approximately in the range of 100 clock pulses. Okay. So in the range of 100 clock pulses means like somewhere around 80, 90, 100, 120, etc. Like, so DFT team, we will be able to tell that the counter is failing in approximately in the range of 100 clock pulses, like 80, 90, 100, 120, like that. So if you see, DFT team, we actually require less number of clock pulses as compared to functional verification team. So if you remember, functional verification team, they require more than 1000 clock pulses to tell that the counter is failing. Whereas DFT team, if you see, we are able to tell that the counter is failing in approximately in the range of 100 clock pulses itself, like 80, 90, 100, 120, like that. Approximately in the range of 100 clock pulses itself, we are able to tell that the counter is failing. So if you see, DFT team, we require less number of clock cycles as compared to functional verification team. So that's why test time will be less compared to the functional verification team. Okay, functional verification team, if you see in this case, they require more than 1000 clock pulses to tell that the counter is failing. Whereas DFT team, we are able to tell that the counter is failing in approximately in the range of 100 clock pulses, like 80, 90, 100, 120, like that. In the range of 100 clock pulses, we will be able to tell that the counter is failing. So if you see DFT team, we require significantly less number of clock pulses as compared to functional verification team. So that's why test time will be less compared to the functional verification team. And how is this? How DFT team we are able to tell that the counter is failing in such significantly less number of clock cycles? It's because we will be going for scan insertions. Okay, we'll be doing something called as scan insertion. Because of that, we will be easily able to control and observe our circuit. Okay, we'll be going for scan insertions. Because of that, we will be easily able to control and observe our circuit. So that's the reason why DFT team, we are able to tell that the counter is failing in significantly less number of clock cycles. So DFT team, we implement scan insertion. We go for scan insertion. Because of that, we are able to easily control and observe our circuit. We'll understand about what is called as a scan insertion and how with the help of scan insertion, we are able to easily control and observe our circuit. We'll try to explore it more when we do the DFT advanced course. In the regular course, when we do it, we'll be able to understand. Okay, so DFT team, if you see, we are able to tell that the counter is failing in significantly less number of clock cycles. Okay, and how we are able to tell in significantly less number of clock cycles? Because we are going for scan insertion. Because of that, we are easily able to control and observe our circuit. Okay, and then DFT team, we will be able to tell that the counter is failing. And we will also be able to tell what manufacturing defect has caused the counter to fail. Okay, DFT team, we will be able to tell that the counter is failing. And we will also be able to tell what manufacturing defect has caused the counter to fail. And how we are able to tell that? How DFT team are able to tell what manufacturing defect has caused the counter to fail? So it's because DFT patterns, they are generated using ATPG. DFT patterns are generated using ATPG, automatic test pattern generation. So ATPG tool, it does a process called as fault simulation to generate the test patterns. It does a process called as fault simulation to generate the test patterns. Okay, so that is why DFT engineers will be able to tell what manufacturing defect has caused the counter to fail. And you'll be able to understand this in depth when we do the regular 3.5 months course, when we do it. Okay, when we do the DFT advanced training, the 3.5 months course, when we do, you'll be able to understand this in detail. Okay, so yeah. So this is what, in short, I've just given you an idea about what is the difference between the DFT engineer and then a functional verification engineer. So let me just quickly once summarize it before we proceed further. Okay, so we are just trying to understand why do we need a DFT team when a functional verification team is present. Okay, so for that I'm just taking an example. So in my example, I'm having a design where in my design I'm having a 10-bit counter with a counter initialization and a counter observation circuit. So we'll consider a scenario. So scenario is counter is manufactured with a defect. So that's why after counting to 999, instead of counting 1000, it incorrectly rolls back to 999. So after counting 999, instead of counting 1000, it once again counts 999. We try to understand what will happen if only functional verification team is existing and what will happen if a DFT team exists. So if only functional verification team exists, what will happen? Functional team, they will test the counter with functional patterns. So in that scenario, it will take more than 1000 clock pulses to tell that the counter is failing. And the reason is because functional verification team, they check the functionality. So in this case, the counter is failing at 1000 pulse. So 1000 pulses will be required for this. And some more clock pulses will be required for counter initialization and counter observation. So the counter, it has to be brought to the initial state. And then the output of the counter, it has to be taken to some register. And the register has to be read. So that's why some more clock pulses will be required for counter initialization and counter operation. So that's why functional verification team, it will take more than 1000 clock pulses to tell that the counter is failing. Okay, functional team tests the counter with functional patterns. It will take more than 1000 clock pulses to tell that the counter is failing. And functional verification team, they can only tell that the counter is failing. Again, the reason is because they will be checking the functionality. So in this case, they will check if the counter properly counts from 0 to 1023. So in this example, after counting 999, instead of counting 1000, the counter is again counting 999. So the counter is failed. Okay, so functional verification team, they can only tell that the counter is failing. Okay. So functional verification team, if only functional verification team exists, what will happen in this case? They will take more than 1000 clock pulses to tell that the counter is failing, and functional verification team, they can only tell that the counter is failing. Now we'll try to understand what will happen if a DFT team is there. Okay, if a DFT team is present. So if a DFT team is present, then what will happen? DFT patterns will be used to test the chip. Okay. So in that example, it will take, so DFT will be able to tell that the counter is failing approximately in the range of 100 clock pulses itself. Like somewhere around 80, 90, 100, 120, like that, approximately in the range of 100 clock pulses itself, DFT team, we will be able to tell that the counter is failing. So if you see, DFT team, we are able to tell that the counter is failing in significantly less number of clock cycles as compared to the functional verification team. Okay, so DFT team, we are able to tell that the counter is failing in significantly less number of clock pulses as compared to the functional verification team. So test time will be less compared to the functional verification team. And how DFT team, we are able to tell that the counter is failing in significantly less number of clock cycles? It's because we will be going for scan insertion. Because of that, we will be easily able to control and observe our circuits. And when we do the regular DFT course, when we do the regular DFT course, we'll try to understand about the scan insertion, and we'll also try to explore how with the help of scan insertion, we are able to easily control and observe our circuits. Okay. And then DFT team will be able to tell that the counter is failing. And we will also be able to tell what manufacturing defect has caused the counter to fail. And how DFT engineers are able to tell what manufacturing defect has caused the counter to fail? So it's because DFT patterns, it will be generated by ATPG, automatic test pattern generation. ATPG tool, it does a technique called as fault simulation to generate the test patterns. Okay, ATPG tool, it does fault simulation to generate the test patterns. So because of that only, DFT team, we will also be able to tell what manufacturing defect has caused the counter to fail. Okay, so in our example, if DFT team is also present, then what will happen? DFT team will be able to tell that the counter is failing approximately in the range of 100 clock pulses. So if you see DFT team, we are able to tell that the counter is failing in significantly less number of clock cycles compared to the functional verification team. So test time will be less for DFT. And then DFT team will be able to tell that the counter is failing. We will also be able to tell what manufacturing defect has caused the counter to fail. Okay, so we'll just have a summary over here. So the conclusion is, with DFT patterns, test time will be less compared to the functional patterns. So as we saw in the previous example, so functional verification team, it took more than 1000 clock pulses to tell that the counter is failing in the previous example. Whereas DFT team, we were able to tell that the counter is failing in approximately in the range of 100 clock pulses, like somewhere around 80, 90, 100, 120, like that, some in the range of 100 clock cycles, DFT team were able to tell that the counter is failing. So if you see DFT team, we require significantly less number of clock cycles as compared to the functional verification team. So that's why test time will be less compared to the functional verification team. Sorry, with DFT patterns, test time will be less compared to functional patterns. Okay, with DFT patterns, test time will be less compared to the functional patterns. And DFT will be able to tell what manufacturing defect has caused the chip to fail. Okay, so functional verification team, they can only tell that the chip is failing. DFT team, we can tell that the chip is failing, and we can also tell what manufacturing defect has caused the chip to fail. So if you see DFT patterns, it has these advantages over the functional patterns. So these two are the advantages of DFT patterns. So test time will be less compared to functional patterns, and we will be able to tell what manufacturing defect has caused the chip to fail. So if you see, DFT patterns has these advantages over functional patterns. Okay, so that is why DFT patterns will be used to test the chip after manufacture. Okay, so DFT patterns, it has these advantages over functional patterns. So that's why DFT patterns only will be used to test the chip after manufacturing. So some functional patterns will also be used to test the chip after manufacturing, but majority DFT patterns only will be used to test the chip after manufacturing. Okay, so with DFT patterns, test time is less compared to functional patterns. And DFT team, we will be able to tell what manufacturing defect has caused the chip to fail. So if you say DFT patterns has these advantages over functional patterns. So that's why DFT patterns only will be used to test the chip after manufacturing. Some functional patterns also will be used, but majority DFT patterns only will be used to test the chip after manufacturing. Okay, so this is what is the need of sorry sorry. So this is why we need a DFT engineer even when a functional verification team is existing. Okay, with the DFT patterns, test time will be less. And with DFT patterns, we'll be able to tell what manufacturing defect has caused the chip to fail. So DFT patterns has these advantages over functional patterns. And that's the reason why we require a DFT team when a functional verification team is already there. Okay. Now we try to understand. Now we have understood why do we need a DFT team when a functional verification team is already present. Now we have seen that DFT patterns, it is having these advantages over functional patterns. So the advantages, these two advantages, what I've written in this slide. So DFT pattern, it has these two advantages over functional patterns, and that's why DFT patterns only will be used to test the chip after manufacturing. So if DFT patterns are used to test the chip after manufacturing, then why do we need a functional verification team? Any guesses? Can anyone guess the answer? Okay, so if DFT patterns are used to test the chip after manufacturing, then why do we need a functional verification engineer?
To
Any
check the
guesses?
functionality.
Yes, correct. So if DFT patterns are used to test the chip after manufacturing, why do we need a functional verification team? So yes, as you correctly said, in order to check the functionality. Let's try to understand this with the help of an example. So say for example, we'll consider a simple circuit, a half-adder design we'll consider. So sum is equal to A plus B, carry is equal to AB. So this is not correct. This is a functional bug. So sum should have been A XORed with B, carry should be AB. Okay. But here someone by mistakenly they have written sum is equal to A plus B, carry is equal to AB. This is the functional bug. Okay. For time being, just assume that you don't have a functional verification team. Okay. For time being, assume that you don't have a functional verification team. So if you don't have a functional verification team, then what will happen after this? Directly it will be synthesized. Your design will be synthesized. So it is getting converted into like a structural form or technology node specific gate level netlist. Okay. So if you see this is a wrong design has got synthesized. So A and B it is ORed and that is sum. A and B it is ANDed, that is carry. So this is a wrong design. So wrong design has got synthesized. And then this is what will be given to the DFT team. And DFT team, what do? We will be generating the patterns. And we'll be generating the patterns just to check whether there are any manufacturing defects in each and every net of this design. Okay, so DFT team, we will generate patterns just to check whether there are any manufacturing defects in each and every net of this design. Okay, and after this, the chip has got manufactured. Okay, after this, the chip has got manufactured. And then DFT patterns are only used to test the chip after manufacturing. So DFT patterns are applied and then we get the output of the chip. So output of the chip, it is compared with the expected output. So output of the chip is equal to the expected output. So it means that there are no manufacturing defects. Okay, output of the chip is equal to the expected output. It means that there are no manufacturing defects. But whether this design will function like a half adder, there are no manufacturing defects. But whether the design will function like a half adder? No, it will not function. Even though there are no manufacturing defects, the circuit will not function like a half adder. Why? The design itself was wrong. So here if you see the first stage, the design itself was wrong. So that's why even though there are no manufacturing defects, the circuit will not function like a half adder. Okay, so that is why we require a functional verification team. Okay, so that is the significance of the functional verification team. They validate the functionality. So whatever is written here, whether this is correct or not, that is what will be validated by the functional verification team. Okay, so say for example, I've considered a design. Sum is equal to A plus B, carry is equal to AB. This is a design of a half adder, but you are having a functional bug. Actually, it should have been sum is equal to A XORed with B. But someone by mistakenly, they have written sum is equal to A plus B, carry is equal to AB. Now, for time being, if you imagine that you don't have a functional verification team, directly the design has got synthesized. So this is a wrong design. And then this design is given to the DFT team. DFT team, we will generate the patterns just to check whether there are any manufacturing defects in each and every net of this design. Okay, DFT team, we will generate patterns just to check whether there are any manufacturing defects in each and every net of this design. Okay, and then the chip has got manufactured and DFT patterns are applied. So DFT input sequence is applied and then the output of the chip, it is compared with the expected output. So output of the chip is equal to the expected output, which means that there are no manufacturing defects. But whether the circuit will function like a half adder in this case, there are no manufacturing defects. But whether the circuit will function like a half adder? No, because even though there are no manufacturing defects, the circuit will not function like a half adder because the design itself was wrong. That is what is the significance of the functional verification team. So functional verification team, they validate the functionality. So sum is equal to A plus B, carry is equal to AB. Whatever is written, whether this is correct or not, That is what will be checked by the functional verification team. They will be validating the functionality. Okay. So now we have tried to understand why do we need, what is the difference in the role of a DFT engineer and what is the difference in the role of functional verification engineer. Okay, the differences between the roles of DFT engineer and then a functional verification engineer. And we try to understand why we need both DFT team as well as the functional verification team. Okay, we have also tried to understand why we need both DFT as well as the functional verification team. Okay, so yeah, we will also explore more about this when we do the regular course. Okay, so as of now, I've just given an overview. I've just told you what is the difference between a DFT engineer and a functional verification engineer and why we need both DFT engineer as well as a functional verification engineer. So we have tried to understand this. So we'll explore about this more in our regular course. Okay. Now we'll try to understand what happens during the testing. Okay, we'll try to understand what happens during testing. So in the ASIC flow slide, we had a slide called as testing, packaging and testing. So at that time I told, right, it is actually done after manufacturing. So this testing is done after manufacturing. So testing, it is a process of determining whether a device is good or not. So whether our chip is good or not. That is whether our chip is having any manufacturing defects or not. Okay, so testing includes test pattern generation, application, and output evaluation. Okay, so as you know, these test patterns, as you know, it will be generated by the DFT engineer before manufacturing itself will be generating the test patterns. So it will be consisting of the input sequence and then the expected output. Okay, so these test patterns, it will be generated by the DFT engineers before manufacturing itself will generate these test patterns. So it will be consisting of the input sequence and expected output. So what will happen? This input sequence, it will be applied onto the chip. Okay, the input sequence will be applied onto the chip, and then output of the chip, it will be compared with the expected output. Output of the chip will be compared with the expected output. Okay, so these test patterns, it will be generated by the DFT engineers before manufacturing itself. It will be consisting of input sequence and expected output. So the input sequence will be applied onto the chip and then the output of the chip will be compared with the expected output. So if output of the chip, if it is equal to the expected output, it means that the chip is good. There are no manufacturing defects. Okay, output of the chip, if it is equal to expected output, means it means that the chip is good. So there are no manufacturing defects. Now, if output of the chip, if it is not equal to the expected output, it means that the chip has failed. So there are some manufacturing defects in the chip. Okay, output of the chip. So input sequence, it will be applied onto the chip, and then the output of the chip, it will be compared with the expected output. So output of the chip, if it is equal to expected output, it means that the chip is good, which means there are no manufacturing defects in the chip. If output of the chip, if it is not equal to the expected output, it means that the chip has failed. There are some manufacturing defects in the chip. Okay. So if a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. So why? Because as I told in the previous slide, right, as I had given an overview in the previous slide. So DFT patterns, they are generated using ATPG. An ATPG tool, it will be doing a process called as fault simulation in order to generate the test patterns. So that's why DFT team will be able to tell what manufacturing defect has caused the chip to fail. Okay. So we'll explore about all these things in detail during the regular course. As of now, I'm just giving an overview. When we do the regular course, we'll explore more on all these points. Okay. So if a particular chip fails, so if output of the chip, if it is not equal to the expected output, it means that the chip has failed. So it means that there are some manufacturing defects in the chip. So if a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay. So how? Because DFT team, they generate patterns using ATPG, automatic test pattern generation. So ATPG tool, it actually does a process called as fault simulation to generate the test patterns. Okay. So that's why DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, so and these are the four possible outcomes of testing. Okay, these are the four possible outcomes of testing. Good IC means it has to pass the test. Good IC means it has to pass the test. So if a good IC, if it passes the test, it is called as true pass. Good IC if it passes the test. Okay, good IC if it passes the test means it is true pass. Defective IC means it has to fail the test. Okay, so if it is a defective IC means it has to fail the test. So if a defective IC, if it fails the test, it is called as true reject. Defective IC, if it fails the test, it is true reject. Now, if in case a defective IC, okay, if in case a defective IC, if it passes the test, okay, if in case a defective IC, if it passes the test, it is called as test escape. It's also called as under testing. If a defective IC, if it passes the test, it is called as test escape. It's also called as under testing. And if a good IC, if a good IC, if a good IC, if it fails the test, good IC, if it fails the test, it is called as yield loss. It's also called as over testing. Good IC, if it fails the test, it is called as yield loss. It's also called as over testing. Okay. Sorry. Goal of good testing, it is actually to reduce the test escape and yield loss. Okay, goal of good testing is to reduce the test escape and yield loss. So yield means number of good chips by total number of chips. Okay, yield means number of good chips divided by total number of chips. So goal of good testing is to reduce the test escape and yield loss. So what is test escape? What is yield loss? We have discussed in the above table. So goal of good testing, it is actually to reduce the test escape and yield loss. So yield means number of good chips divided by total number of chips. Okay. And we'll try to understand what is this manufacturing defect. Okay, we'll try to understand what is manufacturing defect. Okay. So manufacturing defect means, okay, so they are the defects that are caused due to process variation and random imperfections. Okay, manufacturing defects means they are the defects that are caused due to process variation and random imperfection. So process variation means slight variation in transistor channel length, metal interconnect width and thickness. So all those things can actually impact the logical and timing performance. Okay, slight variation in transistor channel length, metal interconnect width and thickness. So all these things can actually impact the logical and timing performance. And then random imperfections. Random imperfections means unintentional shorts, unintentional opens. So that is what is called as random imperfections. Manufacturing defects means they are the defects that are caused due to process variations and random imperfections. Okay. And what is the flow of DFT? So flow of DFT means first is insertion. So as you know, we will be adding our own test structures into the design, like scan insertion, embed insertion, boundary scan insertion. Like that, we'll be adding our own test structures in the design. And then we will be having the generation. Generation means patterns will be generated. So the patterns, it will be consisting of the input sequence and then the expected output. Okay. And then we have the validation, that is something with simulation. So simulation, it is actually to validate the patterns that were generated during ATPG. Okay, simulation, it is actually to validate the patterns that were generated during ATPG. So for that, we actually go for simulations. Okay. So in the upcoming slides, we'll try to explore the course outline. What are all the topics will be covered in the in the next during the DFT advanced course. Okay, in the DFT advanced course, what are all the topics will be covered? We will try to explore it. Our course syllabus, the DFT course syllabus, will try to explore it in our upcoming slides. Okay, the course outline will try to explore it in the upcoming slides. Okay. So this is our course outline. So first is we'll be covering scan insertion and then scan compression. Scan compression, it is also EDT insertion. We also call it as EDT insertion. Okay, EDT insertion. And then on-chip clock controller OCC. And then ATPG, automatic test pattern generation ATPG. And then simulations. Then we have JTAG, joint test action group, JTAG, MBIST, memory built-in self-test, and boundary scan. So these are all the topics which we will be covering it in our course. Okay. And now we'll try to explore about each and every point. So we'll try to understand like in each topic, what is each topic. We'll try to see an overview about each stage. Okay, we'll try to see an overview about each stage. And then like what is it? We'll try to see what are all the topics will be covered in each like what are the subtopics which is present in each main topic. We will try to understand it. Okay, so yeah. We can have a break for 10 minutes now, and after the break, we can try to explore more on the course outline, the theory part, as well as the lab part. So, what will be covered in the theory session and what will be covered in the lab session. So, we'll try to have a course outline. So, what are the topics will be covered in our course? We'll try to understand. Okay. So, we can have a break for 10 minutes, and after the break, we can continue with this. Okay. So, so we can have a break till like 3:30. So we can have a break till 3:30. Okay. So thank you all. We'll meet after the break at 3:30. So good afternoon all. We will continue with our session. Am I audible? Can anyone confirm if I'm audible? So yeah, we will continue with our session now. So we'll try to see an overview about each topic which is there in this course outline. Okay. So the first topic is scan insertion. So what is scan insertion? So during scan insertion, what will happen is the normal flops. The normal flops, they will be converted into scan flops. And these scan flops, they will be stitched into scan chains. So this is what is scan insertion. Okay, so the normal flops, they will be converted into scan flops. And these scan flops, they will be stitched into scan chains. Okay, so we'll try to explore what is a scan flop, what is a scan chain, what is the functionality of a scan flop and a scan chain, all those things we'll try to explore it in detail when we do the regular courses. Okay, so as of now, just remember that in scan insertion, the normal flops, they will be converted to scan flops and these scan flops, they will be stitched into a scan chain. So why do we need to do that? Why do we need to convert the normal flop to scan flop? And why do we need to stitch the scan flops into a scan chain? So why do we need to do that? So that is what is the need of scan insertion. So the need of scan insertion is to gain controllability and observability of the design, which means in order to easily control and observe our design, we'll be going for scan insertions. Okay, so scan insertion means all the normal flops in the design, it has to be converted to scan flops, and these scan flops, they will be stitched into a scan chain. And why do we need to do that? In order to gain controllability and observability of the design. Okay, so in order to easily control and observe our design. So the same counter example, if you see, so which we saw earlier before the break. So in our design, we had a 10-bit counter with a counter initialization and a counter observation circuit. Same example which we explored earlier. So counter, it was failing. That is, after counting 999, instead of counting 1000, it was again counting 999. So how many clock pulses will be required by functional verification team and DFT team to find out that the counter is failing? So as we explored earlier, functional verification team, they require more than 1000 clock pulses to tell that the counter is failing. So how? That is what we had already explored it before the break itself. Okay, so functional verification team, they will be checking the functionality. So in this case, counter is failing at the 1000th pulse, because at the 1000th pulse only, instead of counting 1000, it is again counting 999. So 1000 pulses will be required for this. And some more clock pulses will be required for counter initialization and counter observation. So ultimately, functional verification team, it will take more than 1000 clock pulses to tell that the counter is failing. Whereas DFT team, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses, like somewhere around 80, 90, 100, 120, like that. Approximately in the range of 100 clock pulses itself, we are able to tell that the counter is failing. So how are we able to tell in such significantly less number of clock cycles as compared to functional verification team? It is because DFT team, we go for scan insertions. We go for scan insertions. So that is why we are easily able to control and observe our circuit. Okay, that's why we are easily able to control and observe our circuit. So what is scan insertion? Normal flops, they will be converted to scan flops, and scan chains will, and those scan flops, they will be stitched into scan chains. Okay, and why are we doing that? Why are we converting all the normal flop to scan flops and stitching the scan flops into a scan chain? It is done in order to easily control and observe our circuit. Okay, in order to easily control and observe our circuit, we are going for scan insertion. So in this example, if you see, DFT team, we are able to tell that the counter is failing in significantly less number of clock cycles as compared to the functional verification team. The reason is because DFT team, we have gone for scan insertion. So that's why we are able to easily control and observe our circuit. Okay, so that is what is the need of scan insertion. And we'll try to explore this more in detail when we do the regular course. When we do it, we'll try to understand this point in detail. We'll try to understand how DFT engineers, we are able to tell that the counter is failing approximately in the range of 100 clock pulses. How we are able to tell this. All those things we'll try to understand when we do the regular course. When we do the DFT advanced course, regular course, when we do it, we'll try to understand all these points. Okay. In order to understand this, you first need to know what is a scan cell and how it functions, what is a scan chain, and then a functionality of a scan chain. All those things you need to know. So only then you will be able to see that we are able to tell that the counter is failing in approximately the range of 100 clock pulses. Okay. So we will explore about this point in detail when we do the scan insertion topic in our regular course. Okay. So as of now, just remember that scan insertion means all the normal flops, they will be converted to scan flops. And the scan flops will be stitched into scan chains. And we are doing this. We are doing this in order to easily control and observe our circuit. Okay. And as a part of scan insertion topic, what other topics will be covered? So what are the subtopics which will be covered in our scan insertion topic? We'll try to understand. Okay, scan insertion is the main topic. So in that, what are the subtopics will be covered? We'll try to understand. So first we'll be covering like what is a scan cell. Okay, we'll be covering what is a scan cell and its functionality. Okay, what is a scan cell and its functionality, and then what is a scan chain and its functionality. Okay, we'll try to like cover what is scan cell, its functionality, and what is a scan chain, and then its functionality. We'll try to understand, and then we'll try to understand what is the uh, need of scan insertion. What is the need of scan insertion? Okay, so need of scan insertion is actually to easily control and observe our circuit. We'll be going for scan insertion. So that is what we'll once again take up that counter example which we discussed. We will explore that counter example more in detail when we do the course. And by the end of that counter example, you will be able to see what is the need of scan insertion. So we will be easily able to control and observe our circuit. To gain controllability and observability of the design means in order to easily control and observe our circuit, we'll be going for scan insertion. Okay. And next, like what is scan insertion basically? Normal flops, they will be converted to scan flops and then scan chains will be stitched, right? So now if a normal flop, okay, if a normal flop, if it has to be converted to scan flop, if a normal flop, if it has to be converted to scan flop, it has to pass certain rules. It has to pass certain rules. So those rules are called as scan DRCs. Those rules will be called as scan DRCs. Scan DRCs. DRC means design rule checks. Design rule checks. Okay. So there will be various scan DRCs like clock controllability DRC, clock controllability DRC, set reset controllability DRC, potential race DRC, feedback loop DRC, X source DRC, bus contention violation. Okay. So likewise, there will be various scan DRCs. We will explore about all these scan DRCs during the scan DRC topic. So for normal flop, if it has to get converted to scan flop, then it has to pass certain rules. So those rules are only called as scan DRCs. Okay, scan DRC is nothing but design rule checks. DRC means design rule checks. Okay, so clock controllability DRC, set reset controllability DRC, potential trace, feedback loop, X source, bus contention. So these are the various scan DRCs. Okay, and then after this, we will go to a topic called as scan chain balancing. We'll go to a topic called as scan chain balancing. So what is called as scan chain balancing? Keeping almost equal number of flops in the scan chain is what is called as scan chain balancing. Okay, scan chain balancing means keeping almost equal number of flops in the scan chains. Almost equal number of flops in the scan chains. Okay, so that is what is called as scan chain balancing. Scan chain balancing means keeping almost equal number of flops in the scan chain is called as scan chain balancing. Okay, so keeping almost equal number of flops in the scan chain. So that is what is called as scan chain balancing. So say for example, you have three scan chains. Like this is scan chain 1, this is scan chain 2, and scan chain 3. So in scan chain 1, you are having 1000 flops. Scan chain 1 and 2, you are having 1000 flops. Okay, and scan chain 3, you are having 999 flops. If it is like this means, then it is the balanced scan chains. So it means that you are having balanced scan chains. Okay, so you are having almost equal number of flops in the scan chain. So these are called as balanced scan chains. Okay, so that is what is called as scan chain balancing. Keeping almost equal number of flops in the scan chains is called as scan chain balancing. And why? Why do we need to go for scan chain balancing? Okay, so why do we need to go for scan chain balancing? So we need to go for scan chain balancing to reduce the test time. Okay, we need to go for scan chain balancing to reduce the test time. To reduce the test time. Okay, so how if you go for scan chain balancing, you're able to achieve reduction in test time? We will explore it. We will explore it when we do the scan chain balancing topic. Okay, so how if you go for balanced scan chains? How if your scan chains are balanced, you are able to reduce the test time. We'll try to explore it when we do the scan chain balancing topic. We'll explore it in our regular course. Okay, and if you want to achieve balancing, in order to achieve balancing, in order to achieve balancing, okay, in order to achieve balancing, we need to adopt edge mixing and domain mixing. Okay, we need to adopt edge mixing and domain mixing. So in order to achieve balancing, we need to adopt edge mixing and domain mixing. Now, what is called as edge mixing? What is called as domain mixing? And how if you go for edge mixing and domain mixing, you are able to achieve balancing? All these things we'll try to explore it when we do the regular course. Okay, so scan chain balancing means keeping almost equal number of flops in the scan chains. And why do we need to go for scan chain balancing? In order to reduce the test time. Okay, and how if you go for scan chain balancing, you're able to achieve reduction in test time? We will explore it. We will explore it in order, while doing the regular course, we'll try to understand that. And if you want your scan chain to be balanced, in order to achieve balancing, we actually have to adopt edge mixing and domain mixing. So what is edge mixing? What is domain mixing? And how if you adopt edge mixing and domain mixing are able to achieve balancing? We'll try to explore it when we do the course. Okay. So yeah, so now we have seen that in order to achieve balancing, we need to adopt edge mixing and domain mixing. Now, if you adopt edge mixing and domain mixing, it will in turn introduce some more problems. Okay, if you go for edge mixing and domain mixing, it will again introduce some problems. Okay, so what problems edge mixing and domain mixing will cause, and what has to be the solution of the problem? We will try to discuss that. Okay, so like problems in edge mixing and domain mixing, problems in edge mixing and domain mixing. Okay, so we'll see as well as we'll discuss about the solution. Okay, so all those things we will explore. So these are the various various major topics which we will be covering it as a part of our scan insertion course. So apart from that, we will also be covering some more topics like types of scan cells, and then like scan chain reordering, and then like how to control the test enable of ICG, like that. Some more extra topics also we will be covering it. So that we will be doing it in the 6th session of scan insertion. So as of now, I've written the major topics for session 1 to 5, what we'll be covering. That is what we have written. In the 6th session of scan insertion, some more like some definition type questions and some short topics and all we will cover it. Okay. So yeah, that is what this is. What is the scan insertion topic 1 is scan insertion, main topic. And these are all the subtopics which will be covered in the scan insertion topic. Okay, so these are all the subtopics which is present inside the scan insertion topic. Okay. And next is scan compression. Scan compression means a single scan channel is internally divided into multiple scan chains. Or you can say that multiple internal chains, that is the internal scan chains, they are compressed into external channels. Okay, so you'll be having scan chains in your design. You'll be having scan chains in your design. So these scan chains, we will call it as internal scan chains. Okay, these scan chains, we will call it as internal scan chains. Internal scan chains. So these internal scan chains, they will be compressed into external channels like this. So this is nothing but your external channel input, external channel output. Next. So the internal scan chains, they will be compressed into external channels. Okay, internal scan chains, they will be compressed into external channels. So that's what is called as scan compression. And why do we need to do this? Why do we need to go for scan compression? So why the internal chains have to be compressed into external channels? Why do we need to do that? So it is actually done in order to reduce the test time and also to reduce the test data volume. So test data volume means number of bits of patterns. Test data volume means number of bits of patterns. Okay, so test data volume means number of bits of patterns. So we need to go for scan compression in order to reduce test time and also to reduced test data volume. Okay, so how is it like that? So how if you go for scan compression? What is scan compression? Internal change, they are compressed into external channels. So how if you go for scan compression, you are able to achieve reduction in test time and reduction in test data volume? We'll try to explore it logically, okay, during our regular course. During our regular course, we will try to explore this logically. We will also explore this with the help of formula. Okay, so we'll take the formula for test time, we will take the formula for test data volume, we will substitute the values in that formula, and then we will compare with the compression and without compression. We will compare. You will be able to see that if you go for compression, you are able to achieve reduction in test time and reduction in test data volume. So we will cover it when we do the regular course. Okay, logically also we will explain. We will also explain with the help of formula. Okay, both the ways we will try to understand how if you go for scan compression, you are able to achieve reduction in test time and reduction in test data volume. So what is scan compression? Internal scan chains, they are compressed into external channels. Okay. Now, if you're using like mentor graphics tools, if you're using mentor graphics tools, then in order to achieve scan compression, you will be adding a logic called as EDT logic. The full form of EDT is embedded deterministic test. Okay. Full form of EDT is embedded deterministic test. So this is what is the full form of EDT logic. So the full form of EDT is embedded deterministic test. If you're using mentor graphics tools, then you'll be, in order to achieve scan compression, you'll be adding a logic called as EDT logic. So the full form of EDT is embedded deterministic test. Okay. So here in this case, if you see, this is what is your EDT logic. So if you see, these are your internal chains. These are your internal scan chains. Okay. And this is your external channels. These are your external channels. So if you see, in between internal chains and external channels, you're able to see some components like decompressor, compressor, like that. You're able to see some components in between internal chains and external channels. So these are the components of your EDT logic. Okay, so here if you see this diagram, if you see in between internal chains and external channels, you're able to see some components like decompressor and compressor. So these are the components of the EDT logic. Okay, these are the components of the EDT logic. Okay. So as a part of scan compression topic, what are all the things we'll be covering it is? So topic 2 is scan compression. Okay. Topic 2 is scan compression. Okay. So in scan compression, what are all the topics we'll be covering is, first we will try to understand what is scan compression and what is the need of scan compression. Okay, what is scan compression? And then what is the need of scan compression? So need of scan compression, it is nothing but reduction in test time. Okay, so need of scan compression is, one thing is reduction in test time and the other one is reduction in test data volume. Reduction in test data volume. Okay. So how if you go for scan compression, you're able to achieve reduction in test time and reduction in test data volume? As I told, logically also we'll try to understand. And we will also try to understand it with the help of formulas. We'll take the formula for test time, we'll take the formula for test data volume, substitute the values in those formulas, and then compare with and without compression. We will compare how we'll compare with and without compression. We will compare it, and you'll be able to see that if you go for compression, you are able to achieve reduction in test time and reduction in test data volume. Okay, and then we have a quantity called as compression ratio. We have a quantity called as compression ratio. Okay, so compression ratio means number of internal chains divided by number of external channels. Compression ratio means number of internal chains divided by number of external channels. So that is what is compression ratio. Okay, number of internal chains divided by number of external channels. Okay, so this compression ratio quantity, we usually make sure that it doesn't exceed 100x. Okay, we usually make sure that it doesn't exceed 100x. So why do we need to make sure? Why do we need to make sure that this compression ratio doesn't exceed 100x? What problems it will cause if the compression ratio is exceeded above 100x? We'll try to explore it. We'll try to explore it during our course. And we will also try to explore what are the merits and demerits of high and low compression ratio. We'll try to explore about the merits and demerits of high and low compression ratio. So what are the merits and demerits of high and low compression ratio? We'll try to explore. And then we will also try to understand how to decide the number of internal chains and external channels. Okay, we'll try to explore how to deciding the number of internal chains and external channels. Okay, we'll try to understand how to decide the number of internal chains and external channels. And then we will understand about the EDT logic. So as I told, like if you want to go for scan compression, if you're using metagraphics tools, okay, if you want to achieve scan compression, if you're using metagraphics tools, then you need to add up a logic called as the EDT logic. So inside EDT logic, you'll be having these four components. The first one is the decompressor. Okay. Second one is the compressor, or you can even call it as the compactor. Third one is the controller. So inside the controller block, you will be having the mass shift register, mass hold register, Decoders, again decoder also you have XOR decoder, one hot decoder, all those things will be there. Mask shift register, and then mask hold register, then decoder. So decoder you have like XOR decoder, and then one hot decoder. Okay, so these are all the components which is present inside the controller block. Okay, and the fourth component is nothing but this bypass logic. Okay, so these are all the components of EDT logic, and for each and every component we'll explore. So decompressor means what is the structure of decompressor and what role it plays in scan compression. Same way, compressor or compactor means what is the structure of compressor or compactor, what role it plays. Same thing applies for controller and bypass. Okay, we'll understand about the structure of each and every component of the EDT logic, and we'll try to understand what is its role in scan compression. Okay, what is its functionality? We'll try to understand that. And apart from that, we'll also discuss about pipeline flops in compressor. Okay, we'll also understand about pipeline flops in compressor, lockup cells in EDT, all those things we'll try to explore. Okay, so all these points we'll try to explore. Pipeline flops in compressors, lockup cells in EDT. So all those things we'll try to explore. So these are all the various topics which we will be covering it during the scan compression topic. Okay, so in scan compression, these are all the subtopics which we will be covering it. And the next topic is ATPG. So full form of ATPG is automatic test pattern generation. So full form of ATPG is automatic test pattern generation. So as its name suggests, it is a process of generating test patterns for a given fault model. So there will be various fault models like StuckCat, PDF, IDDQ, like that you have various fault models. So ATPG, it is a process of generating test patterns for a given fault model. So during ATPG, what will happen? ATPG, full form of ATPG is automatic test pattern generation. So as its name suggests, during ATPG, test patterns will be generated. And these test patterns will be used to test the chip after manufacturing. Okay, these test patterns will be used to test the chip after manufacturing. So after manufacturing, if suppose there are any defects, these test patterns, it should have the capability to detect most of the manufacturing defects. Okay, so during ATPG, what will happen? Test patterns will be generated. So these test patterns only will be used to test the chip after manufacturing. After manufacturing, if suppose there are any defects, means this test pattern should have the capability to detect most of the manufacturing defects. And how are we sure that our test patterns will be able to detect most of the manufacturing defects? So it's because our tool does fault simulation to generate the test patterns. Okay, it is because our tool does fault simulation to generate the test patterns. Okay, so ATPG is automatic test pattern generation. As its name suggests, test patterns will be generated. And these test patterns only will be used to test the chip after manufacturing. And these test patterns should be having a capability. What is the capability? If suppose there are any manufacturing defects, these test patterns should have the capability to detect most of the manufacturing defects. Okay, after manufacturing, if suppose there are any defects, these test patterns should have the capability to detect most of the manufacturing defects. And how are we sure that our test patterns will be able to detect most of the manufacturing defects? So how are we sure about it? It's because our tool does fault simulation in order to generate the test patterns. And what are all the topics we will be covering it during our ATPG topic is? So we will be covering what is ATPG. Okay, we will cover what is ATPG. We will also cover about fault simulation. Okay, what is ATPG and what is fault simulation we will cover. And fault simulation is actually not a very straightforward topic. So we will take various illustrations and we'll try to explain about the fault simulation topic. Okay. So fault simulation is a process which the tool does in order to generate the test patterns. Okay. And then we will try to understand about fault modeling. So we'll try to understand what is fault modeling and we'll try to understand various fault models. So in fault models, we'll try to understand what is stuck at fault model. We'll be understanding about stuck at fault model. TDF means transition delay fault model. And then PDF, it is nothing but path delay fault model. And then IDDQ. All these things we will understand. So this TDF and PDF, it is called as at speed test. At speed test. Okay. So the TDF and PDF, it is called as the at speed test. And then we will also discuss about fault categories. Fault categories. Okay. Like fault dominance, fault equivalence, and fault collapse. Okay. And then we'll also try to understand about the fault classes. So fault classes, faults, they are broadly classified into two. One is testable and the other one is untestable. So under the untestable, again, you have some subclasses like unused, tied, blocked, redundant, like that you have some subclasses. Inside testable, you again have some subclass like detected. Again, detected means you have to detected by simulation, detected by implication, like that. Same way, possibly detected, and then ATPG untestable, okay, and then undetected. So all these. So if it is ATPG untestable means again you have the subclasses like pin constraint, cell constraint, wire, sequential depth, masked primary outputs, MPO, etc. You have various subclasses of this ATPG untestable class. So likewise, like we'll explore about all the classes as well as its subclasses during the fault classes topic. Okay, and we'll also try to understand about uh, like uh, the test point insertion, test point insertions, pattern classification. Okay, so pattern classification is like what is serial pattern, what is parallel pattern, what is chain pattern, what is capture pattern. Okay, so likewise we'll try to understand about the pattern classifications, and then we'll try to understand what is fault aliasing. Okay, we'll try to understand what is fault aliasing. Okay, And what else? We will also try to understand about the structure of on-chip clock controller. On-chip clock controller, which is nothing but OCC. Okay, so like we will try to yeah, the main thing. What is coverage? Okay, what is test coverage? What is fault coverage? Okay, and then theoretically we will understand about like what is coverage, what is test coverage, what is fault coverage. All those things theoretically we'll understand it in the theory session. In the practicals we will try to focus on coverage analysis and coverage improvement. So like if your coverage is low, you need to see why your coverage was low. So that is what is called as coverage analysis. And you need to do something in order to improve your coverage. So that is what is coverage improvement. So we'll focus on coverage analysis and coverage improvement during our labs. Okay, in the theory, we'll just try to understand the concept of coverage. What is test coverage, what is fault coverage, we'll understand. And in the labs, we'll focus on coverage analysis and coverage improvement. Okay, so and what else we will explore? So like ways of detecting TDF faults. Okay, so ways of detecting TDF faults. So like one will be the LOC, other one will be the LOS. Okay, so LOC means launch on capture, LOS means launch on shift. Okay, so what are these techniques? And then like if you go for LOS technique, then you need to enable the pipeline scan enable architecture. So what is the pipeline scan enable architecture? We'll try to understand. And then we'll also try to understand uh, what else we'll see. Hmm. We will try to understand what is called as a dead cycle. Okay, what are dead cycles? We'll try to understand. And then this false path and multi-cycle path, timing exceptions. Timing exceptions like false path, multi-cycle path. Okay, false path and multi-cycle path. So what will happen? So how it is taken care in stuck at, okay, how it is taken care in stuck at, taken care in stuck at. Okay, so like what will happen in TDF? What will happen in
Screen is not visible.
TDF? Is my screen not visible to everyone? Like in my other device, it is visible. Uh, can others confirm whether it's not visible for everyone? Is my screen visible? Am I audible? Is my screen visible? Like I'm like my screen is visible in the other device. Can anyone confirm that if my screen is visible or not?
Yes, it's visible.
Okay. So like I think the person who said that the screen was not visible, you are facing some network issue, I think. You can just log off and log in through a different network, so you'll be able to it might get resolved. So yeah, these are all the things. These are all the topics which we will be covering it during our what is it? During our course, we will be covering all these topics in ATPG. So ATPG, it is actually like a very vast topic, and it is also not a very straightforward topic. Okay, ATPG is also not a very straightforward topic. So it will take some time, like it might take around 1 month to 1.5 months to cover this ATPG topic alone. Okay, 1 to 1.5 months it will take in order to cover the ATPG topic alone, like around like 6 to 7 weeks it might take. So around 12 to 14 sessions. Okay, 12 to 14 sessions it might take in order to cover this ATPG topic, because it's a very vast topic and ATPG is also not a very straightforward topic. So it will take some time to cover. So it might take around like 12 to 14 sessions it might take in order to cover the ATPG topic. Okay. So yeah, these are all the things which we'll be covering it in our ATPG topic. And then simulations. So simulations, it is actually to validate the patterns which was generated during ATPG. Okay, simulations, it is actually to validate the patterns that was generated during ATPG. So before delivering the patterns generated during ATPG to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that is what is called as simulations. Okay, before delivering the patterns generated during ATPG to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that is what is called as simulations. It is to validate the patterns which was generated during ATPG. Okay, we'll try to understand the need of simulation. We'll try to understand the need of simulation, and then we'll try to understand the flow of simulation, and then basically what is simulation, what exactly happens in simulation, what is simulation, need of simulation, flow of simulation, and then like what is parallel and serial simulation. Okay, so serial and parallel simulation. Okay, and then like what else, analyzing the waveforms, and like so simulation mismatch debug. So if in case your simulation fails, then how to debug the simulation mismatches. So that is what simulation mismatch debug. So all these things will be covered during the simulations. Okay, so in simulation topic, we'll be covering what is simulation, what is the need of simulation, what is the flow of simulation, serial and parallel simulation, how to analyze the waveform, simulation mismatch debug. So if your simulation fails, how to do the debug, what is the procedure to debug it. So all those things we will explore when we do the simulation topic. Okay, so simulation, we will be covering the theory and practicals simultaneously we will cover. Okay, so we will explore the concept of simulation by practically doing it in the labs. Okay, we'll explore the concept of simulation. All these things we will explore it practically while doing it in the labs. Okay, so yeah. And basically in simulations, you have two simulations. One will be the no timing simulation. Okay, one is the no timing simulation. And the other one is the timing simulation. So one is the no timing simulation and the other one is the timing simulation. So in our DFT course, we will be covering only no timing simulation. So this is what is covered in our DFT course. Timing simulation, it is not covered in the DFT course. Okay, timing simulations are not covered in the DFT course. The reason is, in order to do timing simulations, we require a file called as SDF file, standard delay format SDF file is required. So the SDF file is not available for the test case which is there in our institute. So that's why in DFT course, we will be covering only no timing simulations. timing simulations will not be covered in the DFT course. Okay. So if in case you require some exposure on timing simulations as well, if in case you want to learn about timing simulations also, if you need some training on timing simulations as well, you can check with the institute management. So like if possible, they will let you know if it would be possible or not to cover the timing simulations. Okay, so you can just tell if in case if you want some exposure on timing simulations as well, then you can contact the institute management. They'll let you know if it would be possible for them to provide you some training on timing simulations or not. So as of now, we will be covering only the no timing simulations. In our DFT course, we will be covering only the no timing simulations. Timing simulations will not be covered. As of now, in our regular DFT course, timing simulations will not be covered. Okay. So if in case you want some exposure on timing simulation as well, then you can check with the institute management. They'll let you know if that would be possible or not to provide some training on timing simulations. Okay. So, and the next is JTAG. So the full form of JTAG is Joint Test Action Group. Full form of JTAG is Joint Test Action Group. So it's a IEEE 1149.1 standard. Okay, it's a IEEE 1149.1 standard. So why do we use JTAG? We use JTAG in order to minimize the number of ports from top level and also to achieve boundary scan. We'll be making use of JTAG in order to minimize the number of ports from top level and also to achieve boundary scan. So let's try to understand how with the help of JTAG we are able to minimize the number of ports from the top level. So here in this case, if you see, I have kept a list of some important signals. So memory bypass enable, EDT bypass enable, int mode, X mode, inteltesimal, exteltesimal enable, like that. I've kept some 5 to 6 signals. I have kept it, right? So these are some of the list of some important signals. These are a list of some important signals. There will be many more signals like these. Okay, these are a list of some important signals. There will be many more signals like this. Now, if all these signals are to be controlled from the top level, so which means if you allocate a top level port in order to control memory bypass enable, one top level port to control CDT bypass enable, one top level port for the int mode, X mode, so on. If you allocate a top level port in order to control each and every signal, then what will happen? The number of top level ports will increase drastically. Okay. So here I have just kept a list of some important signals. There will be many more signals like these. Now, if all these signals are to be controlled from top level, which means you are allocating a top level port in order to control each and every signal, means the number of top level ports will increase drastically. The number of top level ports will increase drastically. So that's why we make use of JTAG to internally control these signals. Okay, that's why we will be making use of JTAG to internally control the signals. Okay. So that is why with the help of JTAG we are able to minimize the number of ports from the top level. So that's why with the help of JTAG we are able to minimize the number of ports from the top level. Okay. So like during the JTAG, what all the things we'll be covering is we'll be understanding like about the will be like with the help need of JTAG, we'll understand need of JTAG. And then we'll also try to understand like what is the difference between static signal and dynamic signal. Difference between static signal and dynamic signal. Static and dynamic signal. Okay. So like with the help of JTAG, we will be able to internally control the static signals. Okay, with the help of JTAG, we'll be able to internally control the static signals. So now what is the difference between static signal and what is the difference between dynamic signal? We'll try to understand with the help of some examples. Okay. And then we will also try to understand the JTAG tap architecture. JTAG tap architecture. And then we'll try to understand about the JTAG FSM. We'll try to understand about the JTAG FSM. So JTAG controller, we'll try to understand about the JTAG controller. So this JTAG controller is only a 16-state FSM. JTAG controller will be a 16-state FSM. Okay. So there will be various states. There will be 16 states in that JTAG controller FSM. So like test logic reset state, run test IL state, and then you have a set of DR states, you have a set of IR states. Like that, you will be having 16 states in that FSM. So we will try to explore about each and every state of that 16-state FSM. And while we are understanding this, we will simultaneously try to understand how with the help of JTAG you are able to internally control the static signals. Okay, so using JTAG, so we will also simultaneously we will explore how with the help of JTAG we are able to internally control the static signals. Simultaneously, we will explore how with the help of JTAG we are able to internally control the static signals. Okay, so we'll understand about the JTAG controller. JTAG controller is a 16-state FSM. We'll understand about the various states which is there in that FSM. And while we are understanding the states of that FSM, we will also simultaneously we will explore how with the help of JTAG we are able to internally control the static signals. Okay, and then we will also cover like IEEE 1687 standard. IEEE 1687 standard is IJTAG. Okay, IEEE 1687 standard is nothing but IJTAG. So I have not included it here in the demo session because like in order to understand what is this IEEE 1687 standard IJTAG, you first need to understand about this JTAG TAP architecture, all those things you need to understand. So that is why I haven't included that in the demo session, but we will be covering it in our course. So we'll be covering this IEEE 1687 standard IJTAG. Okay. So we will try to understand, we will do a comparison between JTAG and IJTAG. Okay, we will do a comparison between JTAG and IJTAG, and we'll also try to understand what are the advantages of this IJTAG. Okay, what is the advantage of this IEEE 1687 standard IJTAG? We'll try to understand. Okay, we'll try to understand what is the comparison between JTAG and IJTAG. We'll also see what is the advantage of IJTAG. Okay, and also we will also try to understand how with the help of JTAG you're able to achieve boundary scan. So first let's try to understand what is called as boundary scan. So in this case, chip 1, chip 2, chip 3, they are properly passing the test of DFT, but still the board is failing. So what is it? We'll try to understand. So first what will happen is, okay, so first chips will be manufactured. Okay, so first chips will be manufactured. Okay, and then what will happen after this? Chips will be tested on the ATE. Chips will be tested on ATE. So full form of ATE is automatic test equipment. Okay, full form of ATE is automatic test equipment, we also call it as tester. This is how. This is the AT. Okay, so this is the AT. So what will happen? Chip 1, chip 2, chip 3, they will be tested on the AT like this. So this is chip 1. Input of the chip will be coming from the AT. Output of the chip will be going back again to the AT. Same way this is chip 2 and same way this is chip 3. So input of the chip will be connected to the AT. Output of the chip will be going back again to the AT like this. Okay. And then what has happened? Chip 1, chip 2, chip 3, they have passed their test on the AT. Chip 1, chip 2, chip 3, they have passed their test on AT. Okay. So passed their test on AT means output of the chip, it will be equal to the expected output. Okay. So already in the testing slide, we had seen that, right? In the earlier slides, we had already seen it. So chips will be tested on the AT. We also call it as a tester. So input of the chip will be connected to the AT. Output of the chip will be going back again to the AT. So in this case, consider the chip 1, chip 2, chip 3, they have passed their test on AT, which means output of the chip, it is equal to the expected output. Okay. So which means chip 1, chip 2, chip 3, they are internally not having any manufacturing defects. Okay. They don't have any manufacturing defects. Not having any manufacturing defects. Okay. Now after this, what will happen? After this, okay. So after this, what will happen? Chips will be placed on the board. Chips will be placed on the PCB board, and then the interconnection between the chips and all will be formed. Okay. So the chips will be placed on the PCB board. Like this. So this is the PCB board. So chip 1, chip 2, chip 3, they have actually got placed on the PCB board. And then the interconnection between the chips are formed. Okay. So now after this, what is happening? After this, board is tested. Okay. So after this, what is happening? Board is actually tested and the board is failed. Okay. So after this, board is tested. Board is tested. Okay. So what is happening? It is failed. So why is the board failing? So chip 1, chip 2, chip 3, they have already passed their test on the AT, which means they are not having any manufacturing defects. Then why is the board failing? So it can be due to the manufacturing defects in the interconnection between the two chips. Okay. So this can be due to the manufacturing defects. Due to the manufacturing defects. Manufacturing defects in the interconnection between the two chips. Okay, so this is due to the manufacturing defects in the interconnection between the two chips. Okay, so we basically go for boundary scan. We go for boundary scan in order to test the interconnection between the two chips. Okay, so this is to test the interconnection. Interconnection between two chips. Okay. And these are the topics which we'll be covering it during boundary scan. So like what is boundary scan cell structure, and then what are the modes of operation of boundary scan cell, and we'll also try to understand these three instructions. So sample payload. Okay, we'll also try to understand about the three instructions like sample payload, X test, and bypass. Okay. And then when we actually do these instructions, so the sample preload, X test, bypass, when we do these instructions, you will be able to understand how we are able to achieve boundary scan using JTAG. So one need of JTAG we have seen, right, in order to achieve boundary scan. So when we do those instructions like sample preload, X test, bypass, when we see those instructions, so sample preload, X test instruction and all, when we explore, you will be able to see how with the help of JTAG we are able to achieve boundary scan. Okay, so yeah, that's it. And finally, we have MBIST. So the full form of MBIST is memory built-in self-test. Now, why it is called as self-test? Why it's called as self-test? You'll be able to understand when we do that course, right? In the regular course, when we do it, you'll be able to understand why it is called as self-test. Okay, you'll be able to understand why it's called as self-test. And we use MBIST technique in order to test the memory. So as its name suggests, memory built-in self-test. So we use MBIST technique in order to test the memories. Okay. So what all the things we'll be covering is, we'll be covering like basics of memories. So first we'll cover the basics of memories. Like an overview, we'll just see like what are the different types of memories like RAM and ROM. What are the various like what are the different types of RAM, like SRAM and DRAM. Okay, like that, we'll just have an overview about the memories. We are not going to go in depth about like what is the functionality of a DRAM cell, what is the functionality of the SRAM cell. All those things we are not going to go in depth. Okay, we are not going to go in depth about those things because it's not required for a DFT engineer. Okay, so we'll just try to see an overview. Okay, like what is what is a RAM and ROM, what is like SRAM and DRAM. Okay, what are the differences, how a SRAM cell will look like, how a DRAM cell will look like. So such kind of basics we'll see. We are not going to go in depth to the working of how does a SRAM cell work, how does a DRAM cell work. So we are not going to discuss those functionalities. We'll just see the basics of memories. Okay, because those things going in detail about the functionality of a DRAM cell and functionality of a SRAM cell, it's not required for a DFT engineer. So we'll just see an overview about those things. Okay, and after that, we will go ahead with, okay, after this, we will go ahead with the topics which is required for a DFT engineer. So which means we will discuss about the various memory fault models. We'll discuss about memory fault models. Okay, so like stuck at fault, transition fault, address decoder fault, coupling fault. Again, in coupling fault, you have state coupling fault, inversion coupling fault, idempotent coupling fault. All those things we will cover. Okay, and then memories. Memories, they will be tested using generalized algorithms. Okay, memories will be tested using generalized algorithms. Okay, so memories, they are tested using memories are tested using generalized algorithms. Okay. So we will explore some basic algorithms. Okay, we'll explore some basic memory algorithms like 0-1 algorithm, checkerboard algorithm, and then maths, maths plus, maths plus plus, March X, March C. Okay, we'll try to explore some basic algorithms. So in this algorithm, what we will explain is, okay, so like each algorithm, it will be having a sequence. So we'll try to explore the sequence of those algorithms. Okay, we'll try to explore the sequence. Okay, and then which faults that particular algorithm will be able to cover. Okay, so which faults, like which algorithm will cover which faults in memories. Okay, and how that particular algorithm will be able to cover that fault. We'll explore all those things. Okay, so each algorithm you'll be having a sequence. And which algorithm will be able to cover which faults in memories, we'll try to understand that, and how that particular algorithm will be able to cover those faults in memories. So we'll try to understand it in detail. Okay, with the help of some illustrations, we'll try to understand this. Okay, and we will also try to understand how we are able to test the memories with the help of generalized algorithms. Okay, so that is what how we are able to test the memories with generalized algorithm. We'll try to understand. And afterwards, we will go to Tessent MBIST. So Tessent MBIST means if you want to implement MBIST using Tessent tool. So that is what is called as Tessent MBIST. Okay. So in Tessent MBIST, we will cover. So we'll cover what is Tessent MBIST implementation and architecture. Tessent MBIST implementation and architecture. We will cover Tessent MBIST operation protocol. Okay, we'll understand about BIST setup, MBIST PG enable, and then go, done. We'll understand about all these signals. Okay, while understanding Tessent MBIST operation protocol, right, we'll try to understand about all these signals, like what is a BIST setup signal, what is MBIST PG enable signal, what is a go signal, what is a done signal, all those things we'll understand. And then we'll understand about the group concept, step concept, all those things we will understand. Okay, we'll try to understand about the group concept, step concept. So all these things we'll try to understand. Okay, and yeah, these are the things which we'll be covering it. And in our labs, we'll also focus on, like, if your MBIS pattern fails, how to do the MBIS simulation mismatch debug. So all those things also we will cover. Okay, MBIS simulation mismatch debug also we'll cover it in the labs. Okay. So when you complete the MBIS course, so this MBIS topic, when you complete, at that time you'll be able to understand why it's called as a self-test. Okay, why MBIS is called as a self-test, you'll be able to understand it when you complete this MBIS topic. Okay. So, and whatever I had told earlier, it was in the theoretical part. So in labs, we'll be covering all these things. So IJTAG, MBIST, scan insertion. So there are two approaches in scan. One is the top down and the other one will be the hierarchical scan approach. So we'll be covering both the approaches, EDT and OCC insertion, ATPG pattern generation, ATPG and MBIS simulations. And simulations, as I told, we'll be covering only no timing simulations. Timing simulation will not be covered in our regular course. And boundary scan also, we will be covering it only theoretically. Practicals of boundary scan is not covered. Okay, so I think it's because license is not available for boundary scan. So that's why we are not covering the practicals of boundary scan. So if in case, so in our regular course, we will not be covering it. Okay, in our DFT course, we'll be covering only no timing simulation. Timing simulation is not covered because we don't have SDF file. And boundary scan also will be covering it only theoretically. Practicals we will not be covering because, like, I think we don't have the license for boundary scan. So if in case you want practicals on boundary scan, and then if you want if you want to learn about timing simulations also, then you can once check with the institute management. They will let you know if that would be feasible or not to provide the training on timing simulations and boundary scan practicals. Okay, so in our regular course currently we don't have boundary scan labs, and then boundary scan will be covered only theoretically. Boundary scan labs is not covered, and in simulation also only no timing simulation is covered. Timing simulation is not covered. Okay, so if in case you want practicals on boundary scan as well as timing simulations, then you can once check with the institute management. So they'll let you know if that would be possible for them to provide the training on those topics. Okay, and basically our labs, it will be our labs, it is actually divided into 4 levels. Okay, our labs are actually divided into 4 levels. So level 1, level 2, level 3, and level 4. So level 1 and level 2, they are actually simple labs. So level 1 and level 2, they are simple labs. Okay, so which means like your complexity will be less. For level 1 and level 2 projects, the complexity will be less. Okay, so which means like you'll be having maximum of 100 to 200 flops. Okay, maximum of around 100 to 200 flops. So that's why these are all simple labs. Complexity is less. And then level 3 and level 4 projects, they are designs with higher complexity. These two are designs with higher complexity. Okay, like level 3 projects, you will be having around 4K flops. And then level 4 projects, you will be having around 44K flops. Okay, so these level 3 and level 4 projects, they are the designs with higher complexity. Okay, so this is nothing but this is what is your project work for your course. So level 3 and level 4 projects will be the project work for your course. Okay, so you can write it as you can mention this level 3 and level 4 project as a project work in your resume. Okay, so now in level 1 projects, what we are going to do is we are going to have 11 test cases. And for these 11 test cases, we are going to perform scan insertions. And again, in this 11 test cases, so 2 test cases will actually be to familiarize yourself with the flow. 2 test cases will be to familiarize yourself with the flow. So familiarize yourself with the flow means like if you want to, what is scan insertion? So normal flops, it is converted to scan flops, then they will be stitched into scan chains. So if you want to implement it with the help of tools, if you want to implement it, then you'll be having a set of steps which you need to follow. Like you have a setup phase, analysis phase, insertion phase, like that you have various phases. And in each phase, you need to follow certain steps. So what are those steps? In order to familiarize yourself with that. So we'll be having 2 test cases. What are those steps? In order to familiarize yourself with that, you'll be having 2 test cases. And you are also new, you will also be new to the tool environment, right? So test and tools means that tool environment you'll be new. So how to, you like, in order to to familiarize yourself with the tool environment, and then like how to use the visualizer schematic, how to use it, and then like some basic tool commands, what are the tool commands which is there. So in order to familiarize all those things, you'll be having 2 test cases. And then the remaining 9 test cases, you'll be having DRC violations. You'll be having DRC violations. Okay. So what are DRC? So if a normal flop, if it has to be converted to scan flops, it has to pass certain rules. So those rules are only called as DRCs. So in the remaining 9 test cases, you will be having some DRC violations will be there. Okay. And basically there are 3 methods to clear off the DRC violations. Okay. So 3 methods to clear off the DRC violation. One is like manually editing the netlist. So that is one method. And then with the help of some commands, you can use certain commands like create instance, delete connection, create connection. You can use those commands in order to clear off the DRCs. And you can even there is also auto fix method. There is also auto fix method with which you can clear off the DRCs. So we'll understand about all these methods to clear off the DRC, and we'll try to do a comparison between all these methods, and we'll also see which one is more preferred and why it is more preferred. So we'll try to understand that. Okay. And then we will also try to, like, the tool will be dumping out the files, right? So output files it will be writing out. Okay, scan insertions, it will dump out the output files of scan. So we will also try to explore those output files. What are the output files which the tool has dumped? So we'll try to explore that. Okay, so this is what we are going to do in the level 1 projects. In level 2 projects, what we are going to do is for the same 11 test cases, we are going to perform EDT, ATPG and simulations. We are going to perform EDT, ATPG and simulations. So in EDT, again, you're going to understand the flow. So if you want to perform EDT insertion, then you need to follow certain steps. Okay, if you want to do the EDT insertion using tools, you need to follow certain steps. So what are the steps? So that flow, what is the flow of EDT insertion, we'll try to understand. And same way, if you, so there's some DRCs which you encounter at the time of EDT insertions. So what are they and how to take care about them. So those things we'll try to see. Okay, some DRCs at the time of EDT insertion we will understand. And then we will also open the EDT structure in the schematic. We will also explore the output files. Okay, and we'll try to correlate whatever we have done practically. Then we'll correlate it what we had seen it with the theory session. Okay, we'll correlate the practicals and theory part. Okay, whatever we have seen in the theory session, we'll try to see the same in the practicals. Okay, same way ATPG. ATPG again, there will be a flow. Okay, so if you want to do ATPG, then you need to follow certain steps. Okay, so that is what is the flow of ATPG. We'll understand the flow of ATPG. And ATPG in our labs, we will be generating the patterns for stuck-at fault model, transition delay fault model, and IDDQ fault model. So for these fault models, we will be generating the ATPG pattern. Okay, we will also be generating patterns with TDT and bypass patterns. Okay, we'll be generating patterns with TDT as well as bypass with TDT, and then bypass patterns we'll be generating. Okay, and we will also discuss, like, mainly we are going to focus on, as I told, we'll be focusing on coverage analysis and improvement. Coverage analysis and improvement. So if you're what is coverage, all those things, the theoretical concept, we'll understand it during the theory session. So coverage analysis, if in case your coverage is low, so why is your coverage low? In order to analyze that, that is what is your coverage analysis. And coverage improvement, we need to do something in order to improve our coverage. So like we need to do test point insertions. So again, test point insertion also, either you can manually edit the netlist and you can do it, or else you can do with the help of some tickle scripts, or else you can, there is an automatic flow in testnet with which you can do the test point insertion. So yes, all those things, so those things we'll be able to explore, okay, when we do the ATPG topic. And then we will also what else? Other methods with which you to improve the coverage, like increasing the sequential depth. So what is sequential depth? How if you increase the sequential depth, you are able to improve the coverage. So such kind of things we will explore it. Okay, we'll explore mainly on this coverage analysis and coverage improvement. Okay, in our ATPG labs. We'll also explore about some violations like tracing violations. We'll try to explore all those things. Okay. And simulations, whatever I told earlier, only as I told, theory and practicals, will be doing it simultaneously. Okay, so like whatever I had told earlier, need of simulation, what is simulation, flow of simulation, serial and parallel simulation, simulation mismatch debug steps, that is what we are going to cover here also. Okay, analyzing the waveform, all those things. Okay, so and yeah, and level 3 and level 4 projects. So level 3 and level 4 projects, as I told, they are designs with higher complexity. So level 3 projects will be doing the hierarchical scan approach, and level 4 projects we are going to do the top down approach. And level 3 and level 4 projects will be covering the complete flow. So if you see in level 1 and level 2 projects, we didn't do the IJ tag and embed insertion, OCC insertion, all those things was not covered in the level 1 and level 2 projects. But in level 3 and level 4 projects, we'll cover everything. Okay, so this is the flow. This is the flow which we'll be following it in our level 3 and level 4 projects. So which is nothing but IJ tag and embed insertion. Then EDT OCC insertion. Okay, IJ tag and embed insertion, EDT OCC insertion, synthesis, then scan, ATPG, and simulations. So if you see the complete flow, all the steps will be covering it in the level 3 and level 4 projects. In level 1 and level 2, we did not do IJ tag and embed OCC insertion, or we didn't do, but in level 3 and level 4 projects, we'll cover everything, like IJ tag and embed insertion, EDT OCC insertion, synthesis, scan, ATPG, simulations, everything we will cover. And also in this level 3 projects is actually a hierarchical scan, right? So while doing hierarchical scan, we will also cover some concepts like scan wrappers. Okay, scan wrappers, and then in test, X test, Okay, in test, X test, pattern retargeting. So all these things we will cover. Okay, so when we are doing the hierarchical scan approach, right? So we will also cover these concepts like scan wrappers, in test, X test, pattern retargeting, all those things also we will be covering. Okay, so yeah. And these are the tools which is available for DFT. And in our course, we will be making use of the Mentor graphics tools. So for Embist, we'll be making use of Tessent Embist. For scan, we'll be making use of Tessent Scan. For scan compression, we'll be making use of Tessent Test Compress. ATPG also, we will be making use of Tessent Test Compress. Simulation will be making use of Questasim. So at one point, we need to do the synthesis. So synthesis alone will be making use of the synopsis tool, which is the design compiler. Okay, synthesis alone will be making use of a synopsis tool, which is nothing but the design compiler. For all the other steps, we will be making use of the Tessent tools, metagraphics tools. Okay, Tessent Embist, Tessent Scan, Tessent Test Compress for compression and ATPG, and then for simulation, it will be Questasim. So synthesis alone, at one point we'll be running the synthesis. So at that time alone, we'll be making use of the synopsis tool, which is the design compiler. Okay, so these are the tools which we'll be using it in our course. Okay, we'll be making use of the metagraphics tools, and only for synthesis we'll be making use of the synopsis tool, which is design compiler. And yeah, so these are the topics, like what are the topics we'll be covering it in our course, I had told, right? So apart from this, some more extra topics also I'll just cover it. So like it's not there in our course, but some of the previous batch students have actually requested for those topics. So I will just cover it for your batch as well. Okay. So certain extra topics, like I'll be covering IEEE 1500 standard. I'll give you an overview about these things. Okay, I'll just give you an overview about these topics. IEEE 1500 standard, and then RAM sequential, ROM embed, K rules, F rules. Okay, likewise. So these are some of the extra topics which I will be covering it. So these are not there in our syllabus, but the previous batch students had actually requested. So I'll just give you an overview about those things as well. So IEEE 1500 standard, RAM sequential, ROM embed, K rules, F rules. I'll give you an overview about these things. Okay. And apart from yeah, so like apart from this, I will also cover the static timing analysis, STA over. So STA is nothing but static timing analysis. So it's not a DFT topic, but we'll just have an overview about. So some DFT interviewers, they expect some basic knowledge on STA. Like I'll cover like what is setup time, what is a hold time, what is a setup violation, what is hold violation, and then some problem kind of questions like if your interviewer gives a circuit and if he asks you to find what is the maximum frequency of operation, or he might give you a circuit and ask you to find like whether there is any setup violation or hold violation in the circuit. So such kind of questions, like what are all the questions, like what is latency, what is skew, what is jitter, what is uncertainty, and then like what is removal time, what is recovery time. So such kind of basics we'll just cover it in the STA. Okay, STA overview. Like at the end of the course, I'll just give you an overview about the STA concept as well. Okay, it's not a DFT topic, but some interviewers, they ask some these kind of questions in the interview. So what kind of questions you can expect in the interview for STA? So those kind of things we'll have an overview about it. Okay, and yeah. So whatever I have discussed earlier, so whatever topics like scan, compression, whatever I had told earlier, right? So all those topics, it is covered during the DFT advanced course. Okay. So DFT advanced course topics we discussed earlier. So it will be a 3.5 months to 4 months course. Okay, so it is nothing but all the topics which we discussed earlier in the previous slides. Discussed in previous slides. Okay, and then first you'll be having the DFT basics training. First you'll have the DFT basics training. Okay, so before the DFT advanced course, you'll be having DFT basic course. So this DFT basic course, it will go for 2 to 2.5 months. So in the DFT basic course, so they will be covering digital design, Linux, Tickle, Verilog, CMOS, all those things will be covered in the DFT basics part of the training. Okay, and GVIM, all those things. So GVIM, digital design, Linux, Tickle, CMOS, Verilog. So all these things will be covered in the DFT basics course. So first you have the DFT basics course, which will go for around 2 to 2.5 months, and these are the topics which will be covered there. And after that, you will be having the DFT advanced course, so it will go on for 3.5 months to 4 months. So all the topics, whatever I had discussed in the previous slide, like scan, compression, ADPG, simulation, all those topics, it will be covered. Okay. And apart from this, like after covering each topic, I will also cover a list of like set of application oriented interview questions which is asked in that particular topic. Okay, we'll discuss about some application oriented interview questions which the previous batch students had faced. So that also we will try to cover after each and every, after completing each topic, right? After completing each topic, we'll also like explore some of the application oriented interview questions which the previous batch students had faced. So these are all the application oriented interview questions which we will discuss it during our course. Okay, so these are all the difficult interview questions or application oriented interview questions which we'll be discussing. So if you see, this is for scan, these are all the application oriented interview questions. Okay, so like apart from what is covered in our course, apart from what we do in the sessions, so apart from that, some application oriented interview questions which was faced by the previous batch students. So that also we will cover it. Like these are the application oriented questions which was asked in the previous batch students for scan. This is for scan compression, and these are all for ATPG. This is for simulation. This is for JTAG. Like that for each topic, I have collected a list of some application oriented interview questions which is faced by the previous batch students. So we will discuss all these questions also along with the answers. Okay, so after completing each topic, say for example, after completing scan, we will also try to explore on the application oriented interview questions which was covered for the previous batch students. Well, sorry, which the previous batch students had faced in their interviews. So we will also we will explore the answers to those questions as well. So after completing each topic, we will try to focus on the application oriented interview questions which the previous batch students had faced in that particular topic. Okay, and we will also, by doing this, you will be able to get an idea about what kind of application oriented interview questions you can expect in the interviews, and how to tackle those application oriented interview questions in the interviews. Okay, if you get similar kind of question in the interview, how to tackle it, so you'll be able to get those knowledge. Okay, you'll be able to get an idea about the application oriented interview questions which you can get, and if in case you get any questions like that, how to tackle it, so you will be able to get an idea about it. Okay, And yeah, so who can attend this course? So if you're a student in the final semester and you're seeking DFT as your course curriculum, yes, you can attend it. Or else you're a new college graduate from relevant branches of engineering and science. If you want to attend this course, then you can also attend. Lecturers or professional professors, you want to switch to real-time industry experience means you can attend this course. And even working professionals from similar or other VLSI domains, like you're in design team, for example. If you're in physical design team and you want to shift to DFT means you can attend this course. Or else you're in IT sector but you want to shift to VLSI means you can even attend this course. Okay. And placement support. So we are having tie-up with various VLSI companies, and you will be entitled to placement support based on the performance in your course assignments. So during the course, we'll be giving some assignments, tests, mock interviews, presentation sessions, like that. We'll be conducting some activities. So based on that, you'll be based on your performance, you'll be given the job opportunities. Okay. And mock interviews also will be conducted so that you'll be able to face your original interviews with the confidence you'll be able to face. So that's why we will also be covering the mock interviews. Okay. And so as I told, previous company interview questions and preparations. Okay. So uh, like direct interview question, direct questions also you can get it in the interview. That we will be doing it in our course while we are doing the regular course itself. We will cover those direct interview questions. Direct questions also you can get in the interviews. Yes, that by doing the covering the topic itself, we will cover those questions. And then, like as I told, after completing the topic, we'll also be focusing on application oriented interview questions. So we will train you with that previous company interview questions and preparation. So previous batch students, what kind of application oriented interview questions they have faced. And if you face those kind of questions, how to answer them. So we'll provide those training. So along with question as well as answer, we'll discuss it so that you'll get an idea, sorry, on how to tackle those questions. Okay. And yeah, that's it from my side. And do you have any questions? So let me just check the chat box. Which tool do we use? Yeah, I think I have answered that question. So Mentor Graphics tools. Okay, we'll be making use of the Mentor Graphics tools. So is there any age limit? You can once check that with institute management. So they will let you know if there is any age limit or not. So as far as I know, there is no age limit, but you can once confirm it with the institute management also. Okay, please confirm it once with the institute management also. Okay. Yes, online class. So if you enroll it for weekend only training means during the weekends you will be having the sessions. If you enroll it for full week training means then you will also be having the sessions on the weekdays. Okay. So computer science, whether you can attend this course, even that I'm not very sure. Can you once check that with the institute management? Okay. So in their website, you'll be having their numbers. So you can just check that with the institute management. So as far as you know, like if you're there in ECE or E&I, you can attend this course. Computer science, you can once get it clarified. Okay. You can once confirm it with the institute management. Okay. Uh, Whether I'll be taking both weekend and weekday batch, can you once check that with Manohar sir? So Manohar sir or Bhargavi ma'am, I will share with you those numbers. I'll share with you their numbers. So they will only be allotting the trainers for the batch. It differs from one batch to the other batch. So some batches I might take weekends as well as weekdays. I'll be the trainer. For some batches, I'll be handling only weekend and weekdays will be handled by another trainer. So it depends from one batch to the other batch. So for your batch, how it will be there, I'm not sure. So I will share with you Bhargavi ma'am and Manohar sir's number. So you can check with them. No, so they will let you know the trainers whom they will be allotted. Okay, one second, I'll share with you the numbers. And if you have a career gap of 2 years, whether you can attend. Like one second, I will share with you the numbers, and I'll also tell to whom you need to contact. You can once clarify to them. One second. Uh, Regarding, let me just post it in the chat box. So regarding sessions or trainers, okay, regarding sessions or trainers, you can contact either Manohar sir or Bhargavi ma'am. I will forward their numbers. One second. Timings also, like, it will differ from one batch to the other batch. Okay, so timings also, it might differ from one batch to the other batch. So regarding sessions, trainers, or timings, okay, so it differs from one batch to the other batch. So you can contact either Manohar sir. I will like share with you his number. One second, I'm just typing in the chat box. One second. Or you can contact Bhargavi ma'am. One second. Okay. Regarding sessions, when the sessions will be conducted, so whether it will be weekdays or weekends, so those kind of queries, or else who will be the trainers, so those kind of queries, as well as the timings for the session. So these things, it will differ from one batch to the other batch. So Manohar sir or Bhargavi ma'am will be allotting the sessions. So I've shared with you their number. Um, okay, and then queries regarding regarding uh, career gap, career gap, and then what is age limit, and then what is uh, like um, department, department, for example, computer science, CSC, or next students. Okay, whether you can attend, whether you can attend. So for that, you can contact Vaibhav sir. I'll share with you his number. He will be able to give you a correct guidance. One second. Okay. So you can contact Weber sir regarding the career gap, or regarding the age limit, or like whether you can if you're a CSE or mechanical student, so whether you'll be able to attend the course. So you can contact Weber sir. Okay. And also regarding placements also. So placements also, you can contact Weber sir. If you have any doubts regarding placements also, you can contact Weber sir. Okay, or else you can directly in the institute website, you will be having their numbers, right? So you can even directly contact their that numbers also, or else you can contact the numbers whatever I have shared. Or if you have a individual group with your VLSI Guru ID and a VLSI Guru name, if an individual group is there means, so in that individual group you can post it. So they all these faculty will be there in that group and they will be able to address the appropriate questions. Okay. So my name is Vidisha. Okay. So my name is Vidisha. So any other questions?
Ma'am, can we get your number for any doubts regarding the...
Yes, like you'll be having an individual group which is created. Okay, so like once you enroll into the course, an individual group will be created with your VLSI Guru ID and your VLSI Guru name. So I'll be in that group. So you can post your queries in that group, and we will be able to address that. Okay, so when individual group will be created with your VLSI Guru ID and your name. So in that group you will be there. I'll also be there, and also Manohar sir, Bhargavi ma'am, Bebo sir, they will also be there. So if you get any queries related to technical doubts, if you post it in that group, I will be clarifying it. Or else some non-technical doubts like whatever I have posted in the chat box, right? So if you get those kind of non-technical doubts, then the respective faculties will address that. Hard copy of the notes, yes, they will share with you the hard copy of the notes. So once you complete the payment of full fees, so they will be sharing with you the hard copy notes. And apart from that, soft copy notes of each session will be shared. So hard copy notes, like you'll be having an overview of it. Okay. And each session, the detailed notes of each session that will be shared to you in soft copy, over a soft copy through a Google Drive, it will be shared. And you will also be having access to it throughout your life. In that Google Drive link, you will be able to have the access. Okay, so hard copy notes, like overview notes will be shared. Okay, overview kind of notes will be shared uh, to you, and detailed notes of each session, it will be shared to you as a soft copy. Okay, through the Google Drive.
Ma'am, will we get today's recorded class?
Yes, you can contact Manohar sir. He will provide the recording. So demo session alone, I think they will be providing you the YouTube link. After that, when you go to the regular course, so your each each day's training, it will be uploaded in the InSkill portal. Okay. So demo session alone, they will be providing the YouTube link. So if you request Manohar sir, he will give you the YouTube link. Do we need laptop for the first 2 months of the course? So yes, in order to do that GVim, Linux, Tickle, in order to do all those things, you will require laptops will be required. Okay, and you can also confirm that with Manohar sir also. Okay, actually you require the laptop, so you need to work on Linux, GVim, Tickle, all those things you need to do it, right? So those are all in the computer only you'll be doing it. Okay. And also Verilog, all those things also you'll be doing it in your computer room.
Ma'am, when we get credentials for the tools, ma'am?
After completing the basics course, so when the advanced course is going to get started, they will share with you the credentials.
Okay, ma'am, thank you.
So any other questions you have? Okay, so thank you all. We will end today's class. So if you have any questions, you can contact through the numbers which I have posted in the chat box, or else you can even contact the number which is available in the institute website. Okay, so they will be able to guide you further. Okay, so yeah, thank you all. We will end today's class.